All right, this week we're talking about sediment transport and how sediment is moved through a system in sediment transporting environments. So this lecture is going to particularly focus on rivers, but the processes and a lot of the descriptive terms that we'll talk about here will be relevant and applicable in other sediment transporting environments. So to start off, we can define sediment transport simply as the processes by which sediment is moved through a system and the amounts of sediment that move through a system, right? And so these systems we're talking about here are rivers, turbidity currents, wind, coastal environments, tides, etc. All of those can be sediment transporting environments. In this case, typically the sediment is being transported by a fluid that is acting on that sediment, whether that fluid is air or water. Sediment can also be transported by ice, but that's a little bit more complicated and a little bit less describable in these terms. Okay, so we can just start off by thinking about the initiation of sediment motion and what actually causes a grain to move. And so here's a video from a really cool experiment. You can see a marble here that is protruding above the bed, and you can watch as the flow moves around it and underneath it. So the background here is water that has been seeded with microspheres or particles that are the same buoyancy as water, so that they can track the flow of the water across this experiment here. It says in a flume, and then it's being illuminated or backlit. I believe in this case it's being illuminated by a sheet laser. And so you can see as you watch this video that the fluid up high in the flow is moving really fast, and the fluid near the bed is moving really slow, and that is a function of the friction that is acting on the fluid by the bed, right? So this bed, which has rough particles on it, spheres in this case, is going to impart a friction or a drag on that fluid that's going to slow it down near the bed. And because it has some viscosity, there's some profile of velocity, so the average velocity increases in some way as you go towards the top of this flow. And then you look at the sphere itself here that's protruding above, and you can see a couple of things happening, right? Let's let it go back here a little bit before it starts to move. You can see that the flow over the sphere is moving faster than the flow that may be sneaking around under the sphere, right? You can see that there's a turbulent wake that's forming behind it, but there's also a sort of a backwater, if you will, that's formed in front of it. So you can see the flow is slowed here, and it's fast here, and then it's chaotic and sort of slowed down behind here. So there's a couple of processes that are acting on this grain that are eventually going to cause it to start to move, okay? And so we kind of want to think about what those processes are and what those forces are for any given grain in a flow, because that's going to set up how a fluid can start to move sediment. At what point does it start to move a grain of sand or a grain of gravel or something like that, okay? So we can look at a force balance on a grain, which might look something like this. This is a force balance, if you've taken a physics course, is the typical way you start to think about these problems of motion, right? When all forces are balanced, then a particle is not able to accelerate, right? And so in this case, the initial condition of the particle is at rest, and so you have to overcome the force balance of this particle in order for it to start to roll. So as you look at a figure like this, you can see again, this is sort of the descriptive version of what we saw in that last video here. So this is the velocity profile here. So u, lowercase u, is the local mean velocity at some elevation, right? and you can see that it's very low towards the bed, and then it increases in some nonlinear way as you go up in the flow, right? And you can see again there's the turbulent eddies at the back of the channel, or at the back of the particle, sorry, and gravity is holding down this grain. And the different forces that will occur in order to move this grain out of its location are as follows. First, there is a lift force that is exerted on the particle, right? The particle can experience lift as a function of the fact that the velocity towards the top of the grain is faster than the velocity towards the bottom of the grain, right? And if you imagine from, if you've ever taken a physics course and thought about the Bernoulli lift, that's the component that we're referring to here, in which a pressure gradient exists because the flow is moving faster over the top than over the bottom. It's the same thing as like an airplane wing, right? The reason an airplane wing is designed as a flat bottom and then a curved top is so that the same flow has to go faster over the top than under the bottom of the wing, and that causes that lift. The same thing occurs on a particle protruding into a flow that has some profile like this, okay? So that would be a force that is causing a vertical lift on that particle, okay? There's also a component of lift that can be generated as velocity, as turbulent eddies impinge upon the bed in the upward direction. So if you're looking at a turbulent eddy, sometimes it can be pointing downwards at this location, and sometimes it can be pointing upwards. And sometimes if it points downwards right here, it can exert a pressure in this direction as it fluctuates. So those are very complicated, but those slightly larger than the particle turbulent eddies can, in some instances, result in an upward velocity being directed towards that particular particle that can eject it from the bed, right? So that is one component that can also exert an upward velocity component to the or an upward force on the particle, okay? But it's not just the vertical component that matters, right? So we're sitting here, most grains are not cubes, and so they're not going to sit perfectly stacked on top of the bed, right? So a typical grain is going to be tried to lift out of a pocket, right? So there might be two grains sitting here and a grain inside. So there's a lift force that is trying to pull it up off the bed, and it also has to, there's also a drag force that's trying to roll it over and out of that pocket, right? If you can imagine if it was a sphere sitting on a perfectly flat surface, it would be very easy for a flow to move it along the bed with just a slight amount of drag force and not very much lift force, right? But because it's sitting down in that pocket, it needs to have some lift to get it either up out of that pocket or a significantly larger amount of drag to get it to roll up over the grains that it's resting inside of. Does that make sense? So if you have two grains sitting here like this, and the particle is resting inside, it has to overcome this slope once it starts to move, right? And sometimes that can be 30 degrees or more, right? Which is significant. So you also have drag forces then that can be exerted on the particle to help it, in conjunction with the lift forces, roll or pop up out of that pocket, okay? And those drag forces occur because of a couple of different processes. And these two terms that I'm about to give you will be actually relevant in the context of other processes in sediment transport as well. The first one being what we call skin friction. And this is the friction of the fluid moving in almost in like a laminar sense around the particle itself, right? So you can imagine, just as there was a friction exerted on the bed, or by the bed on the flow, there's a friction exerted by the grain itself, okay? So as the water flows or the air flows around that particle, there's going to be some friction based on it, just its contact with a rigid body, such as the grain, right? So we call that skin friction, and that will exert a drag in the downstream direction, okay? The second form of drag that can be exerted by the particle on the fluid or the fluid on the particle, right? Those are equal and opposite. Friction forces are equal and opposite. Is called form drag. And form drag is a little bit interesting. Form drag occurs in turbulent flows when you have, just as we had a fast-moving flow and slow-moving flow exerting a pressure gradient which caused the particle to want to lift. In this case, you also get these turbulent eddies here at the back of the particle. So as the flow moves over, you end up with sort of detachment or separation of flow here, and then the eddies kind of circle back in, if you will, in behind this particle. And what that does is that results in a low pressure zone at the back of this grain. Okay, so just those turbulent eddies being back here and sort of pushing their way back in there results in low pressure on that side of the grain relative to high pressure on this side of the grain, which exerts its own drag force. Okay, so pressure gradients across a particle result in a drag force. The same will be true when we start talking about bed forms in the next lecture. Okay, and this is true in particular when we start thinking about this is turbulent flows, which are represented by what's called a high Reynolds particle number. That's just a descriptor of turbulent potential or turbulent energetics of a flow. Okay. So those are sort of the things that can conspire, if you will, or combine to result in the movement of a particle. Okay, and oftentimes all of those individual forces, right, can be approximated, if you will, by a term we call shear stress. Okay, and shear stress is the force that's imparted by the fluid on a bed in the direction parallel to the bed. Okay, so this is a term that we can calculate from various other ways that tells us how much the fluid is exerting a stress on the bed that is then becoming available to move those grains of sediment, right? And so in order to start that particular process moving, in order to start a particular grain moving, you have to exceed a certain amount of shear stress, which imparts a lift force and a drag force, right? In order to get that particle to start moving, and also in order to maintain movement across the bed, okay? Because as you impart a stress, the act of moving sediment also extracts momentum from the flow. So there's a balance that gets created by the stress that results in a certain amount of sediment in transport, okay? Shear stress is the term that we use to describe how momentum is exchanged between the fluid and the bed. Okay, so it's an equivalent but not exactly the same term as momentum. So if you've taken a physics course, stress is the term that we use to imply the amount of momentum that is exchanged at that interface between the sediment and the fluid. Okay, so that's how much is shearing at the bed between the friction and the drag of the bed exerted on the fluid, or the friction and drag of the fluid exerted on the bed, which will be equal and opposite. Okay, and it's that stress, that shearing, that is responsible for sediment transport. Okay, and shear stress is often denoted in rivers in particular, but also in other systems as the Greek letter tau here. So this is tau B is the bed shear stress or the boundary shear stress. You'll often see it denoted this way in sedimentology literature. And it is a force per unit area right? A stress is a force per unit area. And so in this case, it's the force that's applied by the moving fluid, water or air, divided by the area of the bed over which that force is applied, right? And so we can define it in a number of different ways. The first way that I would say is the most convenient usage here is that shear stress is defined as the density of the fluid times this term which we'll call shear velocity squared. Shear velocity is a term that basically describes the near bed turbulent energetics of the flow, right? And you can measure this in a number of different ways, okay? So one of the ways in which you can measure shear velocity, right, is by relating it to the flow velocity and the drag coefficient, or essentially the roughness of the bed, okay? So you can kind of start to think about how all of these things start to relate, right? A fluid moving over a perfectly smooth bed is not going to impart as much stress on that bed because the friction will be lower, right? And that friction is defined or is described by this drag coefficient, right? And so in that case, the fluid velocity may be high, but the drag coefficient will be very low because the bed is very smooth, and so your shear stress exerted on the bed might be lower in that case. Does that make sense? So you can start to see how all of these terms become interrelated that way. All right. And this term becomes important, this concept of shear stress becomes important when we start to think about how different fluids can move sediment in different ways, and in particular how a fluid begins to move sediment, right? And it's really this term of shear stress that defines when sediment starts to move and also how much sediment moves once it begins. Okay, so as we kind of referred to earlier, there's a term we call the critical shear stress, and it is the stress that is applied by the fluid on the bed at the initiation of incipient motion, right? So when particles just start to move downstream is when we say we've exceeded the critical shear stress for that size of grain. This is a cool video of a spherical particle with a camera inside, and you can see that if we go back here for a second, you can see, I don't know if it's perceptible on your screen, but the flow velocity is increasing through this experiment. You can kind of see it as the undulations on the water surface start to get faster. You can see the grain start to wiggle as it's starting to come out of its pocket, right? And at a certain flow velocity, the grain wiggles a little bit and then it can just go. And once sediment begins moving, it's a lot easier to keep it moving, okay? So that's why this notion of critical shear stress is really important, is that particles or sediment has a threshold, if you will, and it's set by the fact that it's, that they're a grain of a certain size that takes a certain amount of stress to move, that no sediment moves. You can ramp up the stress, ramp up the stress, ramp up the stress, and no sediment will move, and then all of a sudden the sediment can start to move, and that's that critical shear stress component, okay? And we call that, we call those threshold systems. So you'll often hear the term threshold of motion used in this case, right? And you'll hear threshold systems discussed a lot if you've, say, taken a geomorphology course or other kinds of courses. And so this term critical shear stress and the discussion of this term date back all the way to the 1930s, and we'll talk about this paper by Shields and this diagram called the Shields diagram, in which case the initiation of bedload motion, which we'll talk a little bit more about what bedload is specifically, is a function of the grain properties, which we can describe by what I mentioned earlier as the particle Reynolds number, which is sort of a proxy for grain size, if you will. It includes the grain size in it. It's sort of the hydrodynamic grain size. It's how the grain behaves in terms of its size in a fluid of a particular viscosity is what the particle Reynolds number is. And a dimensionless version of the shear stress. So you non-dimensionalize the shear stress for convenience and for other physical reasons, and can refer to it as, you'll see it referred to as the Shields parameter or the Shields stress. That's the non-dimensional version of shear stress. Okay, and when you plot a bunch of data from experiments, and this is what Shields did in his, I believe it was a 1936 dissertation actually. There's some really interesting stories associated with his dissertation and how he got stuck where he was in 1930s. That if you plot the point at which all of these particles of different sizes and different densities start to move, you can see that there's a consistent pattern in the critical shear stress from all of these experiments, right? And you can see that here. This is his original data set from experiments where he had different types of grains with different densities. You can see that those written here, and you can see, so he has amber, coal, granite, sand, etc., right? And you can see that over all of these different densities and grain sizes, you get a pretty consistent smooth curve here for when the grains start to move relative to their hydrodynamic grain size, right, or the Reynolds number of the grain, which is that shear velocity times the grain size divided by the kinematic viscosity is what this term is here, of the fluid, versus the dimensionless Shields stress or dimensionless shear stress here, which is shear stress divided by the density of the particle minus the density of the fluid times the grain size here. Okay, and this is actually a really important concept, and this gets used again and again, and it's been updated and parameterized in different ways, and this is probably the most commonly used version from a paper by an author called Brownlee. This is the Brownlee curve. Again, the same axes here, and you can see that the changes in the shape of this curve actually depend on the turbulent conditions at the bed. So in this case, we have hydraulically smooth, so it's a pretty laminar flow, right? And you get a nice linear curve. And then when you get into this transitional flow regime between smooth and turbulent or rough conditions, you kind of get this weird dip, right? And these are grain sizes around about silt to sand here, so like silt to sand for quartz grains. And this is where most of our sediment transport world lives, right? And then when you get into hydraulically rough conditions around coarse particles, then it's a relatively uniform dimensionless critical shear stress. So that's a really useful concept to think about. And it's important to understand when you go out and look at a river or any sediment transporting system as to why certain particles behave certain ways in the flow, right? And why certain rivers behave different ways. For example, sand-bedded rivers tend to always be above the critical shear stress for that river because you're always down in this low point in the graph, whereas gravel-bedded rivers you might be more commonly transporting just at the threshold of motion. Okay. And then as you get into more cohesive sediments and sediments that are difficult to remove from the bed because they don't protrude very far, right? Turbulence has a really hard time getting around a 10 micron grain, right? Because of the viscosity of water. So as you get into really fine grain sediments in a hydraulically smooth regime, it becomes actually very difficult to initiate that motion. Your critical shear stress goes way high. Does that make sense to everybody? Okay. And what this results in after you've exceeded that critical shear stress is then you ultimately end up in a regime where you have multiple modes of transport that can occur depending on how far above that critical shear stress component that you are, that the flow has exceeded. Okay, and so you'll hear me use throughout this course, especially when talking about rivers and various systems, is a couple of different categorizations of how sediment can be transported in the flow. Okay, and the most common, these are two sort of separate classifications that you can think of on the left and on the right side of the screen. So we'll talk about this first classification here on the left side of your screen, where we've divided the particle motions up in between bedload transport and suspended load transport. So everything derives from the bed material here, more or less, with some exceptions. There's sediment on the bed of the river in most rivers and in all what we would call alluvial rivers, wherein the bed is made up of the material in transport. And a lot of the particles may just be hopping along or rolling along or sliding along the bed. And we call those bedload. Those are the particles that maintain near proximity to the bed, right? So they might hop up and move, a few tens of their lengths, a few tens of their diameter in length downstream, and then do that again, right? That would be referred to as bedload. When you exceed the critical shear stress high enough, right, you can then start to eject those particles from what we call the bedload layer further up into the flow, right? So higher up into the river. And then they can be transported a much longer distance, right? Hundreds to thousands or more times their grain diameter in distance, right? And we refer to that type of transport as suspended load, right? So there's bed load that moves near the bed and suspended load that moves up higher in the flow in suspension, okay? And sometimes you'll hear terms used which are similar but slightly different, in that you'll hear wash load and bed material load used. I use those sometimes depending on the context of what I'm talking about. And in this case, it doesn't refer necessarily to the proximity of the particle to the bed. It actually refers to whether or not the particle ever comes in contact with the bed at all. So in some rivers, like the Mississippi River here out our door, a lot of the particles that are being transported in suspension are so fine that they never settle out and they never, exchange with material on the bed. So you'll have coarse material on the bed and really fine material in the flow. The really fine material that just washes through is called wash load. And everything that can exchange with the bed, the fine sand and medium sand in the river here that can exchange over hundreds of meters or kilometers length scale, we refer to as bed material load. Okay, and so those are just two different ways of thinking about the distinction between the particles depending on the problem that you're looking at. So here's a video of some bed load in transport. I love this video. These are mattresses that I guess fell off of a mattress truck that tipped over in a windstorm here, and you can actually see the I'm going to turn the music off there. You can actually see the various states of particle motion in this video really clearly. You can see that there are some that are rolling, right? I just love, sorry, this is the dorkiest, my favorite bedload transport video ever. You can see some particles that are rolling along the bed, right? Like this one here. Some that are hopping, right? So they get ejected off the bed and then they move some distance. And there's actually a really cool phenomenon here. You can see a feature of bedload is that when a particle gets ejected off the bed, it tends to get ejected almost vertically and then transported at some ballistic trajectory, right? So it goes straight up and then downstream. You can see that with most of these particles. Once they hop up almost vertically, and then they kind of start flowing downstream. This is a classic saltation profile, which we'll talk about in a second. And then there's some that just kind of slide along. And you can see even though for the same flow dynamic system, not all particles are in motion at the same time, right? So some particles come to rest and stay at rest for a minute until they get re-entrained. This is the same as would happen in the bottom of a river. I absolutely love this video of bedload. It's my favorite. So as we kind of mentioned, right, bedload particles can move in a number of different ways depending on the local hydrodynamic conditions. The first way that they can move is simply by rolling along the bed, right? So they can just roll over and just like a beach ball or whatever might do. The next form is called sliding. So a particle, if it's, got an awkward shape or in, just sort of a situation where it's that drag force that's really doing all the work, the particle may slide along the bed for some distance without really flipping over. And that's relatively common, especially at low transport stages, at low shear stress relative to the critical shear stress. And then finally, there's saltation as of the three common ones in bedload transport, where a particle, as we said before, gets ejected up off of the bed and then kind of shoots downstream a little bit as it gets towards the higher velocity parts of the bedload layer, right? And the height of saltating particles, the sort of average height that saltating particles reach, is what's referred to as the height of the bedload layer. And we won't go too much detail into that in this course, but if you take a sediment transport course, you'll hear a lot about that because it's very important for a lot of things. And it'll actually come up a little bit later in this lecture when we start talking about suspended load, because it's the reference height at which we are extracting particles for suspension. Okay. And finally, there's one more mode of transport that can occur for bedload particles, and it's called sheet flow. And that is relatively common in high transport stage environments. It's not terribly common in major rivers. It's not a super stable state, but where the whole bed can move kind of as one sheet of sediment. Okay. Not sure what happened there. So again, with rolling and sliding, it occurs at low transport stages. It's common, especially in coarse grain sizes, like on a cobble-bedded river, for example. And so you can kind of look at some of that. Here's some particles. It's a pretty grainy image. You can see them sort of rolling and sliding. Here's a great example of one that's sliding. It doesn't turn over all that much, and then sometimes it starts to roll. Sometimes it just wiggles along, right? So you can see at low transport stages, that's pretty common. Let's see. Here's what that looks like from a side view, right? Particles are rolling along the bed. Some of the fine particles are being ejected into the bedload layer and saltating, but most of them are just kind of cruising along here, right? So that's rolling and sliding. There's another video of some of that. I love watching the particles kind of wiggle in the turbulence, right? You can see some of these are flattened cobbles, and so they slide a little bit better than roll, like this one right here. Let's see if we can see that come through again. Yeah, that one kind of slid into place here rather than rolled. So that's what that looks like. And it's common again in cobble and gravel bedded rivers, which are typically flowing at or near their threshold of motion. And saltation, again, particles are detached from the bed and are ejected into the bedload layer. And they're well known to follow this sort of ballistic trajectory, like I said, where they kind of shoot almost straight up, and then they get kind of entrained and dragged down down the slope or down the flow. And the reasoning behind this is initially the impingement of turbulence on the bed and the lift forces. In that particular part of the flow, the lift forces are very high at the lowest point in the flow, where the flow is accelerating from where your velocity profile is accelerating from 0 to some higher velocity here. That gradient across that particle is going to be much higher, right? And so it's going to initially eject vertically from the bed, and then as you get further up into the flow, you're going to get into faster and faster parts of the flow as in the sort of downstream direction. So that lift force won't be as high because the gradient of velocity from the bottom to the top of that particle will decrease, but the overall velocity pushing it downstream will increase. And so you end up sort of plucking the particle vertically and then sending it downstream is a very classic trajectory. Here's a great set of photographs of this. These were long exposure, not that long, like order, I think less than a second still, images of front lighted grains in a wind tunnel. And you can see if you were to trace the particle paths here, you can see that a lot of them take an almost vertical trajectory and then they flatten out and smear out. Here's a great example of one of those here, right? And so this is the sketch that this particular author, Bagnold, used in his textbook in the 1940s. These were some beautiful experiments on that, by the way. And so here's a video of some of that, of grains in saltation. You can see in some cases a particle. Let's see if I can find a good one that gets ejected. Here's one that just got ejected. It's going straight up and then it kind of scoots down. Here's another one, right? And you can see that the downstream trajectory is much shallower than the vertical, almost vertical upstream part of the trajectory. Okay, so that's really common with saltating particles. Here's another video of that and slightly higher speed. And one cool thing that you can see in this video, and we just blasted past it, but if you watch, I think it's this particle here, it gets ejected not just by the fluid itself, but by another particle, right? And that's really common in saltating bedload motion, is that particles will often have been ejected by the impact of another particle, right? Where you get a particle that lands on the bed and it might, eject 4 more particles as it does that. And this differs between air and in water because of the various properties of the fluid in particular. Saltating particles in air might have a hop length and height that can be hundreds to thousands of times the diameter of the particle, right? So a grain saltating in air might travel, much higher, for example, than one that might saltate in water. In water, the height might only be 10 particle diameters, whereas the length might be only hundreds of particle diameters. So a relatively small trajectory length relative to air systems. Okay. So and in both of these cases, the speed of the particles, right, is always going to be less than the grain. The speed of the grains is always going to be less than the fluid, right? But that difference is going to be much greater in air. And so think a little bit about why that might be and what processes might result in that as you go through this lecture. Okay. So we can describe saltation trajectories. Again, here's another set of measurements from this, from different experiments. And one thing that you'll see is that relatively consistently, as a function of the height is relatively consistently a function of the height of the bedload layer, right? The saltating particles end up sort of maxing out for any given system. If the flow speed increases, then the height of the bedload layer might increase, but each individual trajectory results in sort of a consistent height and a consistent length. Okay, so they're relatively scaled with one another, which is a particularly useful feature if you're interested in modeling bedload and particle trajectories. This comes up a lot when you're doing sediment transport modeling. I'll kind of leave it there. That's a lot about saltation because it's a really interesting phenomenon. And if you're ever out at the beach, on a windy day when there's sediment moving along the bed, this sounds ridiculous, but I might encourage you to put on your sunglasses or something and lay down on the ground, and you can actually watch grains saltate. You can see them happen in real time. It's actually really neat to see. Okay. Bedload sheet flow, again, as we mentioned, is another version of bedload transport, or another mode of transport. In this case, the entire upper layer of the bedload layer moves as a sheet of colliding particles. It sort of gets fluidized almost, and everything just sort of moves downstream as sort of one sheet. It's a really interesting thing to see. It's not super common to witness in rivers, but it does occur, and you can make it happen in the lab, for example, pretty easily. And that layer is typically, on the order of 5 to 10 grain diameters thick, something like that. So here's a video of that happening, maybe. There we go. So you can kind of see that there are particles that are getting ejected off the top of this flow, but you can see that basically from about here to about here, the entire bed is in continuous motion, right? As the sort of upper surface of the bed is sheared at such a high rate that the particles are all sort of being entrained and colliding with one another, such that the particle motions themselves are what are maintaining particle motions at depth, if that makes sense. Okay. So I would say, if I didn't break this lecture up into two, but if you are watching this at home, this might be a good place to take a break. We're going to start talking about suspended load. Maybe actually what I will do here is I will actually take a break for the video, so it makes it a little easier to download. And then I'll pick up here in a second with suspended load.